Hello and welcome to this revision session for GCSE Separate Science Physics Paper 2. So in this revision session we're going to look at how to answer examination questions on GCSE Physics Paper 2. So if we've been successful and we've learnt in today's lesson, we should be able to answer GCSE Physics examination style questions, assess our understanding of GCSE Physics and understand what topics we need to improve upon for GCSE Physics. So how should you carry out work in this revision session? Well, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this section write down your working out and answers to the question in the revision session. When you're doing this, make sure to write in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So let's have a look at some questions from Paper 2 for GCSE Separate Science Physics. Let's start with the topic of forces. So Figure 9 shows a car travelling at a constant speed on a straight level road. Figure 10 shows a free body diagram for the car. Explain how the free body diagram shows that the resultant force on the car is zero. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to know a couple of things for a free body diagram. The direction of the arrow shows the direction of the force, and the length of the arrow shows the size of the force. So you indicate first that the size or length of the arrow represents the size of the forces. So this indicates to us that the normal contact force is equal in size but has an opposite direction to weight, and then that the air resistance is equal in size but in the opposite direction to the forward force. The next question says, Table 4 shows how the braking distance of a car varies with the speed of the car. A car decelerates from 24 meters per second to 0 meters per second. The work done by the brakes in decelerating the car is 210,000 joules. Determine the mean braking force and give your answer to two significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, the first thing to note is that you're given the work done in this particular situation, and you're also given the braking distance. So you see that you've got a work done and you've got a distance. So if you think of the equations for this exam, the one we're going to be using is work done is equal to force times by distance in the direction of the force. So what the first thing you do is you sub those directly in. So you say 210,000 is equal to F times by 48. It's always important when you're doing calculation questions to sub in the values before you rearrange. We can then rearrange the values to make F the subject. So F is equal to 210,000 divided by 48. So we get 4,375 newtons, but the question said to two significant figures. So you start, your first significant figure is 4, your second is 3, and your third is 7. So what we can say is, because we need to round to two significant figures, the 7 will cause the 3 to round to a 4, so it's 4,400 newtons. The next question says, the braking distance is directly proportional to the kinetic energy of the car. Explain how the data in Table 4 supports this relationship. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, the first thing to realise is you are given braking distance, but you're not given the kinetic energy. You are given the speed of the car, not the kinetic energy. So the first thing to indicate is you know that speed links to kinetic energy with the equation kinetic energy is a half times by m times by v, which is velocity, but that's just speed in a direction, squared. So this indicates to us that the braking distance depends on the square of the speed. So what you need to do is you need to square all of the values of speed in your question. So we do 6 squared, we do 12 squared, 18 squared, 24 squared to get a value which is what was going to be linking in proportionality for the braking distance and the kinetic energy. Now, how do you show direct proportionality when you're given values in a table? Well, you would divide the values in the rows with each other. So you do 6 squared divided by 3, you then do 12 squared divided by 12, you do 18 squared divided by 27, you do 24 squared divided by 48. It's always very important you know how to work out direct proportionality and inverse proportionality from data given to you, and you can prove that they're directly proportional if the value you've gained from all your calculations is the same for each value, and it's important that you do give that conclusion with your work. The next question says, a student investigated how the extension of a spring varied with the force acting on the spring. Figure 3 shows the equipment the student used in a ruler scale between 10 and 15 centimeters. Describe how the student should determine the extension of the spring. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important you can describe what extension is. Now, extension is going to be the final length, the length with the force, okay, acting on it, minus the initial length, the starting length, the length with no force acting on the object. So what you'd do is you'd measure the initial length of the spring. You'd measure the length of the spring when there's no force on it. You'd then measure the final length of the spring when there's a force acting on it, and find the difference between the two values. The next question says, write down the equation which links extension, force and spring constant, and then the extension of the spring was 0.12 meters when the force was 3 meters. Calculate the spring constant of the spring. So pause the video now, then unpause the video when you want to go through your answers. Right, so for this first one, you've just got to know what this equation is, and that is F equals kx, or F is equal to the spring constant times by the extension. Sorry, extension could be given the symbol x or given the symbol e. Now the next question is using the values given in the question into that equation. So the first thing we always ask you to do in questions with equations is to sub the values directly in before you start rearranging. So you'd say, what's the extension? Well, it's 0.12 meters. What's the force? 3.0. So 3.0 equals k times by 0.12. We then rearrange it to make k the subject. 3.0 divided by 0.12 is then equal to 25 newtons per meter. The next question says, figure 4 shows the results of the same investigation using a different spring. The spring constant of the spring was 40 newtons per meter. Determine the energy stored by the spring when the force is 3.6 newtons. Okay, so pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you can understand that to work out the elastic potential energy, which is what the energy will be stored by an elastic spring, and you know that the spring is elastic because the force extension graph is a straight line through the origin, it's directly proportional, is equal to a half times by the spring constant times by the extension squared. So the first thing you need to do is you realize you've got the spring constant, 40, you've got the force, which is going to be 3.6 newtons, but you don't have any extension. So what you can do is you can work out what the extension is, because you go to 3.6 newtons on figure 4, you go up and you read along to see what the extension is. So you read it off to be 9 centimeters, but we don't work in centimeters in physics, we work in meters. So you've got to convert your 9 centimeters into 0.09 meters. You then substitute those values into the elastic potential energy equation, a half times by spring constant times by extension squared, to be a half times by 40 times by 0.09 squared, to get 0.162 joules. The next question says, a student investigated how the acceleration of a trolley varied with the resultant force on the trolley. The force on the trolley was provided by the masses on the spring. Figure 5 shows how the student set up the equipment. This is the method used. Release the trolley from the top of the runway. As the car passed each light gate, a timer turned on and off. The date logger calculates the velocity of the trolley at light gate A and at light gate B. The date logger calculates the acceleration using the two velocities. Repeat steps 1 to 4 using different masses. So which two measurements are needed to determine the velocity of the trolley at each light gate, and why was a sloping runway used instead of a flat runway? So pause the video now, then unpause the video when you want to go through your answer. Right, this first question is pretty much asking you to understand what velocity is. So velocity is measured between the distance it travels between the start of the card and the end of the card, which is the length of the card, divided by the time it takes when the light gates are blocked by the card, because velocity is distance over time. So those are the two values. Now the next thing is, why use a sloping runway instead of a flat runway? You've got to think about why that will be the case. Now if you think about it, a sloping runway isn't going to affect the air resistance on the trolley, because there'll still be the same air hitting the trolley even if it's a slope or if it's flat, and the sloping runway is not causing the trolley to accelerate, because the masses on the string are the thing that's causing the object to accelerate. So the only answer can be to compensate for the effect of friction. The next question says, what are the two advantages of using a data logger and light gate instead of a stop clock in this investigation? So pause the video now, then unpause the video when you want to go through your answer. Right, this question is basically asking you to say, why do we like to use computers and technology and data loggers in investigations? So the first thing to note is there won't be any reaction time error because there's no human starting and stopping the stopwatch, and also the calculations will be completed automatically by the computer in the system, so there's no chance of calculation error by the human. The next question says, write down the equation which links acceleration, mass and force. And then the acceleration of the trolley was 2.4 meters per second squared. The resultant force on the trolley was 1.2 newtons. Calculate the mass of the trolley. So pause the video now, then unpause the video when you want to go through your answer. Right, this first one is just an equation you've got to know, and that is resultant force is equal to mass times by acceleration, or F equals ma. Now for this next question, like we mentioned before, the first thing you do is sub your numbers in. So you check your units, they're fine, so it's 1.2 equals m times by 2.4. We then rearrange it to make m the subject, so it's 1.2 over 2.4, so m is equal to 0.50 kilograms, and we think to ourselves, is that a sensible answer for the mass of the trolley? 500 grams, 0.5 kilograms is a sensible number, so it's likely to be correct. The next question says, figure 13 shows a girl inside a train. The girl is wearing inline skates. The train is moving at a constant velocity. The girl is stationary relative to the train. The girl is not touching the train walls. The train suddenly decelerates. Explain what will happen to the movement of the girl as the train suddenly decelerates. So pause the video now, then unpause the video when you want to go through your answer. Right, this question is all about Newton's laws, and it's the idea of actually Newton's first law of motion, and that is that Newton's first law of motion is that an object will carry on with the same speed and the same direction, it has the same velocity, it has inertia, okay, if there's no resultant force acting on it. Now, because the girl is not touching the train, okay, well, there is no force acting on the girl at any point, so whilst the train will decelerate because there's a resultant force acting on the train, there's no resultant force acting on the girl, so they'll continue to move with the same speed in the same direction, they'll have the same velocity, okay, and they will have inertia because of Newton's first law of motion. It's always important to learn Newton's laws of motion. The next question says, figure 14 shows a velocity time graph for the train for part of its journey. Write down the equation which links acceleration, change in velocity and time taken. Then determine the acceleration of the train between 5 seconds and 11 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, this first one you've just got to learn the equation, and that is acceleration is the change in velocity divided by time, or A is equal to triangle V, delta V, divided by time. Now then what you've got to do is use the graph to work out values. So firstly, you know what the time taken is going to be. If it starts at 5 seconds and goes to 11 seconds, well, the time it takes to go between those 2 points is 6 seconds. What is going to be the change in velocity? So you look for your velocity at 5 seconds, which if you look across is going to be if you look on here, 3.6, and what is it going to be at 11? Well, it's going to be 0, so it's going from 3.6 to 0, so therefore it's changing, it's going down by 3.6. We do minus 3.6 over 6 is therefore equal to minus 0.6 meters per second squared. The next question says, determine the total displacement of the train between 0 and 25 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, it's very, very important that you can work out the displacement from a velocity time graph. Now, the distance travelled in a velocity time graph the distance travelled in the velocity time graph is the area under the line, but displacement is how far the object has moved from the starting point. So what you'll have to do is work out the distance travelled in one direction, the forward direction, which is the area under the line in the positive part of the graph, and then work out the distance moved in the opposite direction, the backwards direction, which is the direction moved, so it's the area under the line in the negative section of the graph. You can then work each one of them out. So what you can do is you can break your area into rectangles and triangles and then work it through. You can then find the forward distance to be 28.8 meters, which is the area under the positive part of the graph. You can then find the backwards distance, which is the area under the negative part of the graph, which is 10.5 meters, and the displacement is the difference between the two, 18.3 meters. The next question says, at a different point in the journey, the train decelerates from a velocity of 40 meters per second to a velocity of 15 meters per second. The deceleration is 2 meters per second squared. Calculate the distance travelled whilst the train is decelerating. So pause the video now, then unpause the video when you want to go through your answers. Right, you can tell straight away that in the previous question we had our displacement, we have our deceleration, which is -2. We've then got, because it's a minus because it's decelerating and slowing down, we've got a final velocity of 15, we've got a starting velocity of 40. So if we've got a starting velocity, we've got a final velocity, we've got an acceleration, and we've got we're trying to work out the displacement, the distance travelled I should have said. We can work it out by doing the equation v squared minus u squared equals 2as, which is an equation given to you in this examination. So the first thing we do is we write out all the values that we know. So we know v is 15, so it's 15 squared, minus u, which we know is 40, so it's 40 squared, equals 2 times by the deceleration, which is -2, times by the distance, s. We then work out both sides to get 1375 equals 4s. We can then work s out to be 343.75 meters. Does that sound sensible for a train moving? Yes, it does, so it's likely to be right. The next question says, figure 15 shows part of the track for the train's journey. The train moves at a constant speed along this part of the track. The train is accelerating. Explain how the train can be accelerating while traveling at a constant speed. So pause the video now, then unpause the video when you want to go through your answer. Right, it's the idea of what acceleration is. So acceleration is the rate of change of velocity, and velocity is always changing. Why is that? Because velocity is a speed in a certain direction. That's just a fact. So when it's going around a corner, even though the speed is constant, the direction is changing, so the velocity is changing, so therefore you have an acceleration. The next questions we're going to look at now are on the topic of waves. So this first question says, figure 1 shows a transverse wave. Which arrow shows the amplitude of the wave? Which arrow shows the wavelength of the wave? So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you've got to learn the different parts of the wave. So the amplitude of the wave by definition is from the midpoint of the wave to either the peak of the wave or the trough, the bottom of the wave. So from our labels, that answer is P, middle to top. Whilst what's the wavelength of a wave? It's the distance between two of the same points on consecutive waves. So on the options given, it's going to be R, because it's from the peak or the top of one wave to the peak or the top of the next wave. So the difference between the two is the wavelength. The next question says, calculate the period of a wave when the frequency was 30 Hz. Give your answer to two significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to know what this equation is, and that's frequency is 1 over time period, so therefore time period is 1 over frequency. As always suggested, put in the numbers first, okay, and so you say it's 1 over 30. So you get an answer in your calculator of 0.033333 seconds. Now you've got to write your answer to two significant figures. So our answer is 0.033. Now why do you have 4 figures there but only 2 significant ones? Because you only start counting your significant figures when you get to your first non-zero number. So those first 2 zeros are not a non-zero number, so don't count. So the first non-zero number you start counting from is that first 3. So the answer is 0.033 seconds. The next question says, a sound wave is a longitudinal wave. The visible light is a transverse wave. Describe the difference between a longitudinal wave and a transverse wave. So pause the video now, then unpause the video and you'll want to go through your answer. Right, it's very important you can learn the definition of these two types of wave. A longitudinal wave is when the oscillations of the wave are parallel to the direction of the energy transferred by the wave. Remember, any wave can be defined in terms of oscillations and energy transfers, because the definition of a wave is a mechanism which oscillates to allow energy to transfer. So a transverse wave is when the oscillations of the wave are perpendicular at 90 degrees to the direction of energy transfer. Let's now have a look at the topic of electromagnetism. Figure 12 shows the equipment a student used to investigate the motor effect. Explain why the wire moves when the switch is closed. So pause the video now, then unpause the video and you'll want to go through your answer. Right, you've got to be able to explain what the motor effect is, which is what this particular situation is showing us. And you've always got to think about the fact that it's to do with electromagnetism. So the first thing to note is that when the switch is closed, the wire has a current flowing through it. Now the principle of electromagnetism is that when any object has a conductor flowing through it, a magnetic field forms around it. So when there's a current through the wire, a magnetic field forms around the wire. So the wire then interacts with the permanent magnetic field of the permanent magnet, because two magnets will either attract or repel each other, and that will cause a force which will cause the wire to move. So write it out step by step. It would also cause the big permanent magnet to move, but not as much because it's got a lot more mass than the light thin wire in the question. The next question says, the student recorded these measurements. Potential difference across the wire is 1.50 volts. The resistance of the wire is 0.60 ohms. The length of the wire in the magnetic field is 0.050 meters. And the force on the wire is 3.75 times 10 to the minus 4 newtons. Calculate the magnetic flux density of the magnetic field. So pause the video now, unpause the video and you'll want to go through your answer. Right, so how do you answer this particular question? Well, we know that F is equal to BIL, where B is the magnetic flux density. But the issue we have, because it's a 6-mark question, is whilst we have F, whilst we have L, we don't have I. And we can work out I because we've got resistance R and potential difference V. So the first thing we know is that V equals IR, so I is equal to V over R. So we do 1.50 over 0.60 is equal to 2.50 amps. And at that point we can put all the values into the F equals BIL equation to say 3.75 times by 10 to the minus 4 equals B times by 2.50 times by 0.050. We then rearrange it and we make B the subject and we work our answer out to be 3.0 times 10 to the minus 3. Now we should always just memorize what the units are for magnetic flux density, and they are Teslas. Now it's important that when you go to 6-mark calculation question, you will be expected to use more than one equation and link them together. The next question says, a wavelength has a wave of 2.5 kilometers and a velocity of 300 million meters per second. Calculate the frequency of the wave. So pause the video now, then unpause the video and you'll want to go through your answer. Right, you've got to be able to know what the wave equation is, and the wave equation is wave speed is equal to frequency times by wavelength. Now the first thing by looking at these values is that the wavelength is in the wrong units because it's given in kilometers and we work in meters. So the first thing we need to do is convert kilometers into meters. So we say 2.5 kilometers is 2,500 meters. We then sub the numbers into the equation to say 300 million equals F times by 2,500. We make F the subject and then we get the answer to be 120,000 hertz. The next question says, figure 14 shows how a solenoid is used in an electromagnetic switch for a door lock. When the switch is closed, the iron bolt is pulled to the right and the door is unlocked. An iron core has been added inside the solenoid. This increases the strength of the magnetic field around the solenoid. Give two of the changes that would increase the strength of the magnetic field around the solenoid. So pause the video now, then unpause the video and you'll want to go through your answer. Right, it's always important to note that you've got to be able to understand what factors affect the strength of an electromagnet. You can tell it's it's about electromagnets because it's a solenoid, which is an example of an electromagnet. Now there are three factors that affect the strength of an electromagnet, and they are the current going through the electromagnet, the number of coils around the iron core of your electromagnet, and it's going to also be the type of core of your electromagnet. Now in the question they've already said that they've added the iron core, so the two other things you could change are increase the current and also have more turns or more coils of wire around your solenoid. Let's now have a look at the topic of space. So the first question says, in 1929 Edwin Hubble made measurements from observations of light of distant galaxies. This light showed redshift. What is meant by redshift? In figure 16 shows how the velocity of distant galaxies varied with their distance from Earth. This graph is based on Hubble's 1929 data. Figure 16 includes a straight line of best fit. Explain why Hubble could not be sure that the velocity of the distant galaxies was directly proportional to the distance from the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing is you've just got to learn what redshift is, and redshift is the observed increase in the wavelength of emitted radiation. Now it's observed because the wavelength itself doesn't actually increase in the wavelength, but we observe it from our point of view that it does. You could have also said that as the shift of the radiation to the redder part of the visible section of the electromagnetic spectrum. Now this next question isn't asking about Hubble's law really, it's asking about how to analyse data. Now you should be aware that direct proportionality is a straight line in your graph through the origin. So why can't you draw a very good straight line of best fit through the origin with this data? Well, it's because there are very few points close to the line of best fit. So there's lots of scatter in the actual data. Now the phrase we would use for variation in data, the correct name is precision. So the data is not very precise because there's a great variation amongst the data. So the line might not actually go through the origin at all, so it's not going to be a straight line through the origin. The next question says, 2 years later, Hubble worked with another scientist called Milton Humason. Figure 17 shows their new data. The age of the universe can be estimated from the equation age of the universe is 975 divided by the gradient of the line in billions of years. Calculate the age of the universe using the data from figure 17. So pause the video now, then unpause the video when you want to go through your answer. Right, this is basically again just analysing data. So the first thing you need to do is draw a large gradient triangle on your graph, and you've got to actually draw the gradient triangle. Now gradient is the change in y divided by the change in x, so the answer should be between 500 and 600. You then plug that value into your equation given in the question, so 975 divided by 550 is 1.8 billion years. The next question says, estimates of the age of the universe have continued to improve. Suggest why. Then Hubble's data led to the Big Bang theory. This is the only theory that can explain the existence of the cosmic microwave background. Explain what is meant by the CMBR. So pause the video now, then unpause the video when you want to go through your answers. Right, this first question is pretty much asking you how have we improved our scientific methodology and our technology over the past over the past 100 years or so. And the idea is we've had improvements in technology. Our telescopes have got better, so we can now take more accurate measurements. Accurate means closer to the right answer, so it's appropriate to use accurate in this situation. Now, what's the CMBR? You've got to know this. It's a fact. It's a form of radiation which fills the universe, which was produced when the matter decoupled in the early universe after the Big Bang and released this radiation. So this radiation came shortly after the Big Bang, 300,000 years after the beginning of the universe. So I hope you've enjoyed this particular revision session, where if you've been successful, you can answer GCSE Physics examination style questions, you can assess your understanding on GCSE Physics, and understand what topics you need to improve upon for GCSE Physics. So thank you very much for watching this revision session on Paper 2 for GCSE Separate Science Physics. Thank you very much and have a lovely day.